I'm Antonio Sala. In this video, we are going to model a tubular heating element as a partial differential equation, which will be infinite order, because we will assume that this tubular heater is the juxtaposition of an infinite number of infinitesimal heating elements. So if we recall the modeling of just one heating element, in which we will assume perfect mixing, so the temperature inside is uniform, then under this assumption, we have three inputs to the system: flow, inlet temperature, and the heating power, Q. Will have some constant parameters: volume, specific heat, density, and we'll have one state variable, the heater element's temperature, capital T, and the objective of the modeling phase is computing the expression of its time derivative. We can take a power balance, and as the flow is incompressible and the element is always filled with fluid, mass does not change, so the internal energy stored there will be mass times specific heat times temperature increments. So in power terms, the derivative of the stored energy will be mass specific heat times time derivative of temperature. Of course, assuming that we are not having phase transitions from solid to liquid or liquid to steam. But okay, so this will be the stored energy in the hot water per unit time, and that must be equal to the sum of three components: the heat transfer with the resistor and the outside environment, the inflow of mass with a given temperature, mass flow will be volumetric flow times density, and then we'll have the outflow. This energy is exiting my control volume, my heater. So we end up with this one element equation saying that the resulting power from mass transport and heat transfer is the amount of power stored as temperature variations of the fluid being heated or cooled, depending on outside temperatures, etc. In this case, we have assumed the outside temperature to be constant and be the origin of coordinates of temperatures and of energy. Okay, so this is the equation of a single element like this. How can we model long heater in which we will actually assume that we have no mixing? So we have a laminar flow from left to right. Well, we can understand such a long tubular heater as, say, the series interconnection of several of the previous elements we modeled. For instance, if we split this in 4 pieces, we can approximate the model of the above by this physical element. Of course, the approximation is due to the fact that we are assuming that in each of the 4 regions the temperature is perfectly uniform, and that's not true. But of course, the trick will be letting the number of elements go to infinite, so the temperature will only be uniform in an infinitesimally small section. That's what we are going to do next. In this case, we have split the heater in 4 finite elements. That's what usually needs to be done in nonlinear simulations if the equations we are going to derive later on have no analytical solution. So finite element is a key aspect of simulations of thermal phenomena, vibrations, electromagnetic waves, okay? But we are going to formally make the numbers of elements infinite. Of course, the volume of each of the elements will be volume divided by 4 in this case. The heating power will be again 1/4 of the total heating power, but the flow will be the same in all elements. So if we have finite elements, we can say that the flow at element I is the same as the flow at the previous element and the same as the flow entering the heater. The volume is just the nth part. The heating power is also its fair share. We divide by 4. And the total power lost to the environment if the whole tube has a heat transfer coefficient of kappa, then half the tube will lose kappa divided by 2 power, and in general, if we divide in n elements, then the heat transfer coefficient will be kappa divided by n. Of course, that's kind of messy, and we will later on introduce some heat loss per unit length bar kappa and heating power per unit length bar q. Conceptually, we are splitting the things in 4, 8, 16, 100, 1 million elements, but we need some changes of notation in order to take limits when n tends to infinity. The next thing we need to realize is that, say, the input temperature to element 3 is the output temperature of element 2, except, of course, for the first element, in which is the actual input to the system, the temperature at the inlet of the heater. Then a finite element model should compute the derivative of each of these 4, 8, or 200,000 temperatures. However, in order to make the elements infinitesimal, we now need to take into account that the temperature actually varies with the position, and in fact, it varies with position and time if the flows and inputs and heating power do change with time. So we will assume that this is the temperature. Then we will assume also that the center of each element is displaced from the center of the next element length, which will be dx. So if element 2 is at position x, then element 3 will be at position x plus dx. In this case, dx will be finite, 1/4 of the total length, but of course, the trick will be making dx infinitesimal. So if we now write the equations of element 3, this is the equation of one element, in which we just took this and divided at the other side. So this is the equation of one element. So element 3 was at position x plus dx, and its input was the temperature of the preceding element, which was located at position x. This thing, temperature of element at x plus dx, will be this thing at instant t. Input temperature will be that of the preceding element, t of xt. Capital T of the element we are considering is this thing. The derivative with respect of time of capital T, when we have one element, now we need to change it to partial derivative, because as temperature depends on two things, then we can take derivatives either with respect to x or with respect to time. So this temporal derivative now will need this new notation. We had a discrete element, so this was ordinary derivative of the temperature of the third element in a fourth order system, but when we now change thinking on this function of two arguments, then we need to change the notation to partial derivatives. So we have all these elements, and now the new notation bar q will denote that the share of heating power corresponding to one element will be the power per unit length times the length of the element, which is dx. And likewise, the heat transfer coefficient for one whole element will be the heat transfer coefficient, or heat loss if the inside fluid is hot, per unit length times the length. Last, volume will be equal to the cross-section times the length of the element. Here we have it, and again, here we have it, the volume. So after all these notational changes, the equation of a finite element is changed to this one, and now we can simplify dx in some places, like here and here, here and here, We also can put this division by dx, dividing there. So this is the final equation. We end up. Our element is still finite. It will be infinitesimal when we compute the limits of these things when dx tends to 0. The number of elements n will tend to infinity when the element length dx tends to 0. So now this time derivative when dx tends to 0 will tend to this if temperature is a continuous function. This temperature over there will also tend to this when dx tends to 0. When arguments are x, t, we just omit them, putting that notation there. And now, when dx tends to 0, this thing is the partial derivative with respect to the first argument, with respect to the position. This is it. So we finish by saying that the limit of this green surrounded equation when dx tends to 0 is this partial differential equation. So we have finished our modeling phase. This is a partial differential equation that relates temporal derivatives and spatial derivatives with inputs, flow, and power per unit length of the resistor. Now, from an engineering point of view, we can say, hey, we had an input to the heater, which was the input temperature. How the hell did it disappear from this equation? Well, it has disappeared from the equation, but it's still there because in order to solve these equations, we need to fix the so-called boundary conditions. And this is the boundary condition that indicates that at any time at position 0, the left extreme of the heater, this must be a known function, arbitrary, determined elsewhere, an input to my equation solver, which is of course the inlet temperature. So even if it's absent from the partial differential equation, we still have the input somewhere in the boundary conditions that are needed to compute a particular solution for a simulation of this heater with suitable formulae. So this finishes the modeling. Nevertheless, there are two particular cases that maybe you will see elsewhere, so we'll quickly tell them which are they. First one is the case of no heating and perfectly insulated pipe. So we have this equation. Then volumetric flow divided the cross section is the linear velocity of the fluid. No. And this is the partial differential equation of the so-called transport delay, whose solution can be shown to be, that what I measure here is just the input temperature that I had some time before, which is the total length divided by the linear speed of the fluid. So this is the solution to the transport delay PDE for constant fluid speed. The second particular case is the equilibrium equation, in which when nothing changes with time, we assume 0 temporal derivatives, and then this is a first order differential equation, let's say, only in the spatial coordinate. Furthermore, if we had no heating, this would be the equilibrium equation of a heat exchanger losing heat or gaining heat power if the ambient is hotter on a pipe. This is also a famous heat exchanger equation because, well, the solution to this is an exponential. So the no heating thermal equilibrium solution is the solution to this equation. So the equilibrium steady state temperature fulfills this equation, in which, of course, the equilibrium temperature no longer depends on time. So this is an ordinary differential equation now because the T depends on only one argument, and of course its solution is an exponential. Initial condition times the exponential of this pole times the argument I am deriving, so it's x position. And of course, the initial condition, as 0 is a position coordinate, it refers to the temperature at the left end of my heat exchanger, so it's the input temperature. So this is a well-known steady-state heat exchanger formula. But again, it's a particular case of our final partial differential equation and boundary condition we derived earlier on in this video. So we'll conclude. In this video, we have modeled this heating element as a collection of several of these elements in which the length of each element is called dx, and we have 400 millions, so dx tends to 0. Thinking now that temperature is a function of both space, length, and time, we get the final partial differential equation that governs this tubular heater. We finally discussed two famous cases, the transport delay and the exponential steady-state heat exchanger solution. So this is it. Thanks for watching.